Tonight, we're going to talk about a lie. Not a deliberate one. Not a conspiracy. A lie told to you by your own eyes every single time you have ever looked up and found that faint, soft smudge of light in the northern sky. You've probably seen it, even if you didn't know what you were looking at. A pale, fuzzy patch, easy to mistake for a smear on your glasses or a trick of tired eyes. If you've ever pointed a phone camera at the night sky and gotten a blurry little cloud in the frame, there's a good chance that's it. The Andromeda Galaxy, the nearest large galaxy to our own. 1 trillion stars away, and yet close enough that on a clear, dark night, you can find it without any instrument at all. But here is what most people don't realize. What you are seeing when you find that soft little smudge is not Andromeda. It is a fraction of Andromeda, a sliver. The bright, compressed, visible core of something so much larger that if your eyes were sensitive enough to see the whole of it, it would not be a smudge at all. It would dominate the sky. It would stretch across a section of the heavens 6 times wider than the full moon. And that's just the beginning of how badly your eyes are underselling it. For decades, astronomers themselves believed they understood Andromeda's size. They measured its bright disk, calculated its diameter, compared it to our own Milky Way, and moved on satisfied. Then they looked closer. They looked with instruments the human eye could never match. And what they found was not a modest correction. It was not a small adjustment to the textbook number. The first surprise was the sky itself. The discovery of just how much of Andromeda's true visible footprint the human eye is physically incapable of registering, even though the light is hitting your retina at this very moment. The second surprise was what lies beyond even that. A stream of stars torn loose from smaller galaxies, stretching far past anything a camera has ever captured in a single frame. The third surprise was the discovery that Andromeda's true edge isn't visual at all. It's a vast, invisible ocean of gas extending so far into space that it is, right now, touching us. Touching the Milky Way. 2 galaxies quietly overlapping, long before a single star from either one has moved an inch. And the fourth surprise, the one that upended 40 years of consensus, is that even the mass of this galaxy, the very thing that defines how big and how powerful it is, was wrong. Astronomers spent decades believing one number, only to discover in a single study that they may have overestimated it by half. By the end of tonight, you're going to understand the true scale of Andromeda. Not the smudge in the sky, but the actual object. Its real visual size. Its true physical boundary. Its invisible reach into the space between galaxies. Its trillion stars. Its monstrous central black hole. And the strange, newly uncertain fate that awaits it and us billions of years from now. Before we dive in, if you're someone who finds peace in understanding the true scale of things, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start with the basics. Not because they're simple, but because even the basics of Andromeda contain more than most people assume. Its formal name is Messier 31, M31 for short, catalogued as NGC 224 by later astronomers, and known for most of history simply as the Andromeda Nebula, before we understood what a nebula actually was and what Andromeda actually wasn't. It is a spiral galaxy, technically classified SASB, a grand design spiral, similar in basic shape to our own Milky Way. Recent infrared observations from the Spitzer Space Telescope revealed something the visible light images had hidden. A bar of stars running through its central bulge, angled about 55 degrees from the long axis of the galaxy's disk. Andromeda, in other words, is not just a spiral. It's a barred spiral, like a pinwheel with a straight rod of stars driven through its center, the arms spinning off from the ends of that bar rather than from the core itself. It sits in the direction of the constellation Andromeda, and it is the largest galaxy in what astronomers call the local group, the small cluster of gravitationally bound galaxies that includes our own Milky Way, the Triangulum Galaxy, and several dozen much smaller dwarf galaxies. Of everything in that group, Andromeda is the anchor, the biggest. The gravitational center of mass around which much of our cosmic neighborhood quietly orbits. But before we get to any of the astronomy, I want you to sit with the name for a moment, because it's older than you might think, and it comes from somewhere unexpected. The story begins with a queen who couldn't stop bragging. In Greek mythology, Cassiopeia, queen of Ethiopia, boasted that her daughter, Andromeda, was more beautiful than the Nereids, the sea nymphs who served Poseidon, god of the sea. It was the kind of boast that gods do not forgive quietly. Poseidon, enraged at the insult to his nymphs, sent a sea monster named Cetus to ravage the kingdom's coastline. Crops failed, ships were destroyed, the people suffered. And when King Cepheus consulted an oracle for a way to appease the god, the answer was as brutal as it was simple. His daughter, Andromeda, would have to be sacrificed. Chained to a rock at the edge of the sea, left for the monster to take. She was still there, chained and waiting, when the hero Perseus happened to fly past. He was returning from a very different kind of victory. He had just slain Medusa, the Gorgon whose gaze turned men to stone, and he carried her severed head with him, wrapped and terrible. Perseus saw Andromeda. He saw the monster rising from the waves toward her, and depending on which ancient telling you follow, he either fought Cetus directly or simply showed it Medusa's face, turning the beast to stone before it ever reached her. He freed her. He married her. And when the story finally ended, when Andromeda and Perseus and the rest of the family had lived out their lives, the gods did something they rarely did. They placed the entire cast of the story into the sky together. Not scattered across the heavens at random, but grouped, as neighbors exactly as they had stood in the story. Cepheus, the king. Cassiopeia, the queen, whose boast started everything. Perseus, the hero. Cetus, the monster, defeated but eternal. And Andromeda herself, still positioned near the edge of the sky, as if still, in some sense, waiting. It is one of the only places in the entire night sky where an entire mythological scene survives intact. Constellation standing beside constellation, telling the same story it told the first stargazers who named them more than 2,500 years ago. And it is from that princess, from that ancient story of vanity and sacrifice and rescue, that the largest object visible to the naked eye in the entire northern hemisphere takes its name. A trillion-star galaxy, named for one girl chained to a rock in a story invented by people who had no possible way of knowing what they were actually naming. That is where we begin. Now let's talk about how we found out what Andromeda actually is. Because for nearly 1,000 years, we got it catastrophically wrong. Here is something that should, by rights, be one of the most famous mistakes in the history of science. And yet almost no one has heard of it. The first written record of Andromeda comes not from Greece, and not from a telescope, because there were no telescopes yet, but from a Persian astronomer working nearly 700 years before one would be invented. In the year 964 CE, Abd al-Rahman al-Sufi completed a treatise called the Book of Fixed Stars, a careful, systematic catalogue of everything visible in the night sky, compiled with nothing but the naked eye and extraordinary patience. In it, he describes something he calls a small cloud near the mouth of a constellation he identifies as the Northern Fish. A faint, soft patch of light, visible only on the darkest and clearest of nights. This is the oldest known written description of a galaxy other than our own. 964 years after the birth of Christ, more than 500 years before Copernicus would even propose that the Earth orbits the Sun, a man in Persia looked up, found a smudge of light that didn't belong to any star, and wrote it down. He had no idea what he was looking at. Neither did anyone else, for the better part of a millennium. In 1612, the German astronomer Simon Marius became the first person to observe Andromeda through a telescope, and what he saw only deepened the confusion rather than resolving it. Through his primitive lens, Andromeda appeared as a soft, diffuse glow. Nothing like the sharp pinpoints of individual stars that a telescope revealed everywhere else in the sky. It looked, to every observer of that era, like a cloud, a nebula, from the Latin word for mist. Something made of gas, drifting somewhere within our own Milky Way, not a separate structure entirely. In 1764, the French astronomer Charles Messier, a man obsessed with cataloguing every fuzzy, comet-like object in the sky so that comet hunters wouldn't mistake them for actual comets, added it to his famous list as the 31st entry, M31, a convenient label, still classified in every meaningful sense as a nebula, a cloud within our own galactic backyard. This misunderstanding did not last for decades. It lasted for centuries. In 1888, the astrophotographer Isaac Roberts took the first photograph of Andromeda ever captured, a genuine technical achievement requiring long exposures and a level of instrumental precision far beyond what any human eye alone could manage. And for the first time, the image revealed something extraordinary, a clear, unmistakable spiral structure. Arms curling outward from a bright central core, exactly the shape you would draw if someone asked you to sketch a galaxy today. And astronomers looked at this photograph, clear evidence of a vast, structured, spinning system, and largely concluded that they were watching a solar system in the process of being born. A young star, they believed, surrounded by a rotating disk of gas and dust that would eventually clump together into planets. The nebula hypothesis, first proposed by Kant and Laplace to explain how our own solar system formed, seemed to explain this perfectly. Andromeda wasn't another galaxy, it was a nursery, a single infant star, nearby, in the earliest stages of building its own planetary system. They had a photograph of a trillion-star galaxy, 2.5 million light-years away, and they thought they were looking at one star being born in our own cosmic neighborhood. This is the kind of confident wrongness that this channel keeps returning to, again and again, because it is never really about the specific mistake. It's about what the mistake reveals, how easily the universe can hide its true scale from instruments and minds that aren't yet equipped to perceive it. The evidence was right there, in the photograph, in 1888. The spiral was undeniable, and still, the true meaning of that spiral remained completely invisible to the people looking directly at it. The disagreement did not resolve quietly. It became one of the most famous confrontations in the history of astronomy, an event historians now simply call the Great Debate. On April 26, 1920, at the National Academy of Sciences in Washington, D.C., two astronomers took the stage to argue, formally and publicly, about the true nature of these spiral nebulae. Harlow Shapley argued that the Milky Way was enormous, so large that it comfortably contained everything visible in the sky, including the spiral nebulae, which he believed were relatively small, nearby objects within our own galactic disk. Heber Curtis argued the opposite, that the spiral nebulae were island universes, entire separate galaxies, each as large as or larger than the Milky Way, at staggering, almost unthinkable distances. Both men were brilliant, both men had genuine evidence, and both men were partly right and partly wrong, drawing careful, reasonable conclusions from incomplete and sometimes actively misleading data. The debate did not produce a winner. It produced a question that would hang, unresolved, for 3 more years, until one astronomer, working alone at a telescope on a mountain in California, found the single piece of evidence that would finally settle it. His name was Edwin Hubble, and the night of October 5th and 6th, 1923, is one of the most quietly consequential nights in the entire history of human knowledge. Hubble was using the 100-inch Hooker telescope at Mount Wilson Observatory, at the time the most powerful telescope on Earth, to photograph Andromeda in painstaking detail, hunting for novae, exploding stars whose brief, bright flares might reveal something about the nebula's true nature. On the photographic plate exposed that night, he initially marked 3 points of light, labeling each with an N for nova. 3 ordinary stellar explosions. Interesting, but not remarkable. Then he went back to check his work, and he noticed something that made him stop. One of those 3 points wasn't behaving like a nova at all. Comparing it against earlier plates, he saw that its brightness rose and fell in a smooth, regular, repeating rhythm. Not the sudden flash and fade of an exploding star, but the steady pulse of something else entirely. A Cepheid variable. A very particular type of star whose brightness rises and falls with a period directly tied, through a relationship discovered years earlier by the astronomer Henrietta Leavitt, to its true intrinsic luminosity. Measure the period of the pulse, and you can calculate exactly how bright the star actually is. Compare that to how bright it appears from Earth, and you can calculate, with confidence, how far away it must be. Hubble crossed out the N on his photographic plate, and in red pencil, in the margin, he wrote 3 characters that would quietly end a 3-year scientific war and reshape humanity's understanding of its place in the universe. VR! Variable star. A Cepheid. And when he ran the calculation, luminosity against apparent brightness, the answer was staggering. The distance came out to roughly 900,000 light years. Not thousands, not tens of thousands, hundreds of thousands of light years. A number so far beyond the accepted size of the Milky Way at the time that there was only one possible conclusion. Andromeda could not possibly be inside our own galaxy. It had to be an entirely separate island of stars, floating in the vast dark beyond the edge of everything Shapley and Curtis had been arguing about. In a single measurement, on a single photographic plate, the universe exploded in size. Overnight, the Milky Way went from being everything, the entire known universe, to being one galaxy among what we now know to be at least 2 trillion others. Hubble's original number, 900,000 light years, turned out to be too small. The Cepheid period luminosity relationship he used had a subtle flaw. There are actually 2 distinct populations of Cepheid stars, with slightly different luminosity relationships, and Hubble's calibration mixed them up. When later astronomers corrected the error, the true distance came out to roughly 2.5 million light years, nearly 3 times farther than Hubble himself had calculated. Still, he had been right about what mattered. Andromeda was not a nebula. It was not a nearby cloud of gas. It was not a solar system being born in our own backyard. It was a galaxy, a separate, vast, ancient island of stars, so far away that the light reaching Hubble's photographic plate that October night in 1923 had left its source when the ancestors of modern humans were still evolving on the plains of East Africa. 964 years of naked eye observation, 300 years of telescopes, and it took one man, one photographic plate, and one crossed out letter to finally tell us what we were actually looking at. You would think, after that, we would finally understand Andromeda's true scale. We did not even close. Because the moment astronomers confirmed Andromeda was a separate galaxy, they made a second assumption, a quieter one that took another 100 years to fully unravel. They assumed that what they could see was the whole story. It wasn't. Here is the number that should, by itself, change how you think about every photograph of Andromeda you've ever seen. The true, catalogued apparent size of the Andromeda Galaxy, the actual angular footprint it occupies in Earth's sky, based on precise measurements recorded in the standard astronomical reference catalogue, is 3.167 degrees by roughly 1 degree, 3 degrees across at its widest. For comparison, the full moon, an object every single person on this planet has looked at directly, an object that feels large and bright and impossible to miss when it hangs low over the horizon, has an angular diameter of just half a degree. Do the division. Andromeda's bright, photographable disk is more than 6 times wider than the full moon. Let that settle for a moment. 6 full moons laid edge to edge in a single unbroken row across the sky, and that row would just barely span the true width of the nearest large galaxy to our own. And here is the part that should genuinely unsettle you. None of that width is visible to your naked eye. Not the 6-moon span. Not even close to it. What the unaided human eye can actually detect, on the darkest and clearest of nights, is only the bright inner core of Andromeda, a patch roughly 1 degree across. about the size of 2 full moons placed side by side. That's it. That's the entire visual experience that led Al-Sufi to write Small Cloud in the year 964. That's the entire visual experience nearly every person who has ever looked up and found that faint smudge has had. 1 degree. 1/6 of the galaxy's actual bright, photographable size. And we haven't even gotten to the parts of Andromeda that no photograph taken with an ordinary camera could ever capture at all. So why does the eye see so little of something so large? The answer is not that your eyes are broken or that you're not looking hard enough. The answer is a piece of physics that most people have never had explained to them. And once you understand it, you'll never look at a faint object in the night sky the same way again. The key thing to understand is this. What your eye perceives is not total brightness. It's surface brightness, the amount of light arriving per unit area of sky. And these two things, total brightness and surface brightness, can be almost completely disconnected from each other. Andromeda's total apparent magnitude, a measure of how much total light reaches Earth from the entire galaxy, is plus 3.44. In astronomical terms, that is genuinely bright. Easily visible to the naked eye under dark skies, brighter than the vast majority of stars you can see on any given night. If all of that light were compressed into a single point, like a star, it would be one of the more striking objects in the sky. But it isn't compressed into a point. It's spread across roughly 3 square degrees of sky, the bright disk alone, without even counting the fainter structures beyond it. All that light, smeared across that much area, means that any single patch of sky within Andromeda's outer disk is delivering only a tiny trickle of photons to your eye. Photons per unit area, surface brightness, is what determines whether your retina actually registers something as a distinct, visible shape. And across most of Andromeda's outer disk, that number falls below the threshold your eye's rod cells can reliably detect. You are, in the most literal sense, looking directly at the light. It is entering your eye right now, if you're outside on a clear night with Andromeda above the horizon. The photons are real. They are striking your retina. And your visual system is simply too coarse an instrument to resolve them into a shape across that much sky at that lower density. There's a second piece to this. Your eye is not a camera. It cannot perform a long exposure. A camera sensor, or a photographic plate like the one Hubble used in 1923, can sit open for minutes, hours, sometimes. In the case of the astrophotographer Robert Gendler's famous ultra-deep image of Andromeda, over 90 cumulative hours, patiently gathering every faint photon that arrives, stacking them, building up a picture of detail that no living eye could ever directly perceive. Gendler's image reveals disk features spanning the full 3-degree width, dust lanes, faint outer structure, all of it real, all of it invisible to any human being who has ever looked at that same patch of sky directly. Your retina, by contrast, effectively resets what it's gathering roughly every 100 milliseconds. It cannot accumulate faint light over time the way a sensor can. Every 1/10 of a second, your visual system starts over, discarding whatever faint signal it had been building. And then there's the third factor, the one most people have direct, personal experience with, even if they've never thought about why it happens. Sky glow. Even modest light pollution, the kind present in most suburban areas, let alone cities, raises the background brightness of the sky itself to a level that swamps Andromeda's already faint surface brightness completely. Only from genuinely dark locations, the kind astronomers rate as Bortle class 1 or 2, truly remote, far from any artificial light, can a careful observer even begin to glimpse hints of the galaxy's outer spiral arms with the naked eye. So here is the honest picture. Hold your fist out at arm's length. Its width, roughly, covers about 10 degrees of sky. Andromeda's true photographable disk occupies almost 1/3 of the width of your own fist. Now hold up just your little finger at arm's length, about 1 degree of width. That's the entire visible portion, the small cloud that Al-Sufi wrote about 1,000 years ago, the 2 moons wide smudge that is all your unaided eye will ever show you. The actual galaxy, if you could somehow see all of it, would be 3 times that width. And we're not done. because even the 6-moon-wide disk that a good camera can capture is nowhere close to the true edge of Andromeda. This is the key that unlocks everything else tonight. Every single popular image of Andromeda you have ever seen, every photograph in every documentary, every image search result, every planetarium projection, shows you, at absolute best, a fraction of the actual object. The rest is invisible. Not because it isn't there, because of the specific, measurable limits of human perception meeting the specific, measurable physics of how light spreads across distance. And once astronomers understood this, once they had cameras and instruments capable of gathering light in ways no eye ever could, they kept looking further out, and they kept finding more galaxy. The 3-degree, 6-moon-wide disk that a serious deep sky photograph can capture is not the edge of Andromeda. It is simply the edge of what a bright, dense concentration of stars produces, the point where the star-forming disk becomes too sparse for even a long exposure to render as an obvious continuous shape. Beyond that boundary, astronomers using specialized wide-field survey instruments, most notably a long-running observational program called PANDAS, the Pan-Andromeda Archaeological Survey, found something that a standard photograph, however deep, simply cannot show. Individual stars scattered thinly, extending the visible stellar structure of Andromeda out to roughly 200,000 to 220,000 light-years from the galactic center. That's already meaningfully larger than the bright disk most images depict. But the true structure extends even further than that, into what astronomers call a stellar halo, or in its most extended and dramatic form, the Andromeda Giant Stellar Stream. This isn't a smooth extension of the galaxy's normal disk. It's something stranger and, in a way, more violent. A long, faint ribbon of stars, torn loose from smaller galaxies that Andromeda has consumed and disrupted over billions of years of its history, stretched out into a curving arc that traces the path of its own destruction. Recent analysis, including work from the PANDAS survey and follow-up studies referred to as PAST, places the outer footprint of this stellar debris, this tidal halo, out to distances of roughly 500,000 light-years from Andromeda's center, 500,000 light-years, more than 3 times the extent of the already far larger than expected 152.00 light-year stellar disk we'll examine in detail shortly. Let that settle for a moment. The bright galaxy you can photograph, 6 moons wide, spectacular, already far larger than anything the naked eye perceives, is contained entirely within a structure that reaches, in its faint outer stellar debris, more than 3 times farther still. A galaxy inside a galaxy, in a sense. A visible core wrapped in an almost invisible shell of scattered, wandering stars, the wreckage of every smaller galaxy Andromeda has ever swallowed. It's worth pausing here to understand what a stellar stream actually represents, because it isn't a gentle or a passive structure. It's a scar. Galaxies, especially large ones like Andromeda, do not grow to their current size in isolation. They grow by consuming their neighbors. When a smaller dwarf galaxy passes too close to a giant like Andromeda, the giant's gravity does not treat it gently. The side of the dwarf galaxy closer to Andromeda feels a noticeably stronger gravitational pull than the side farther away. A tidal force, the same basic kind of physics that raises ocean tides on Earth, but at a scale capable of tearing an entire galaxy apart rather than just lifting seawater. Over repeated close passes, sometimes over billions of years, as the smaller galaxy's orbit decays and tightens, the dwarf galaxy is stretched, elongated, and eventually shredded entirely. Its stars are pulled out into a long trailing stream, some flung ahead of the doomed galaxy's remaining core, some trailing behind, all of them tracing the shape of the orbit the galaxy was following in the final stages of its destruction. Eventually, nothing is left of the original galaxy but this ribbon, a curving trail of stars, still following roughly the same orbital path, now permanently woven into the outer halo of the larger galaxy that consumed it. The Andromeda Giant Stellar Stream is the most prominent example of this process still visible around M31. Direct, ongoing evidence, written across 500,000 light-years of space, of a galaxy in the continuous act of eating its neighbors. It is not ancient history. It is not a single completed event. Andromeda has more than 20 known dwarf satellite galaxies still orbiting it today, and the stream stands as proof of what eventually happens to companions that stray too close. This is not a peaceful galaxy quietly rotating in isolation. It is, and has been for billions of years, a slow-motion predator, patient beyond any human timescale, but relentless. Every stream of stars in its outer halo is a monument to something smaller that no longer exists as its own galaxy, because Andromeda's gravity took it apart, thread by thread, star by star. And this predatory history, it turns out, connects directly to something we'll examine later tonight. A strange, glowing ring of newborn stars deep inside Andromeda's disk, and the violent collision that most likely created it. But first, there is one more layer to Andromeda's true scale. And this one isn't made of stars at all. It's invisible in the most literal sense. And it is, without exaggeration, the largest single structure connected to our galactic neighborhood that anyone has ever measured. Everything we've discussed so far, the bright disk, the extended stellar structure, the 500,000 light-year stream of shredded satellite galaxies, is still, in the end, made of stars. Points of light, however faint, however scattered. What astronomers found next isn't made of stars at all. It's gas. And it is so large that the word galaxy, when you try to apply it to Andromeda's full true extent, starts to feel almost too small. The discovery came from a research program called Project Omega, the absorption map of ionized gas in Andromeda, using the Hubble Space Telescope's cosmic origin spectrograph. The method was elegant in concept, even if it required extraordinary patience and precision to execute. Astronomers cannot photograph invisible gas directly, but they can detect its presence indirectly by using something else as a probe: distant background light sources, whose light has to pass through any gas sitting between us and them on its way to Earth. If that gas is there, it leaves a fingerprint, a subtle absorption signature, in the spectrum of the light passing through it. The Project Omega team selected 43 distant quasars, extraordinarily bright, extraordinarily distant active galactic nuclei, far beyond Andromeda itself, scattered across a wide swath of sky in Andromeda's general direction. 43 separate background flashlights, in effect, positioned at different angles relative to Andromeda, each one capable of revealing, through the exact way its light was subtly altered on the way to Earth, whether Andromeda's gas extended out to that particular point in the sky. The result reshaped how astronomers think about where one galaxy ends and empty intergalactic space begins. Andromeda's diffuse, ionized plasma halo, an enormous, invisible envelope of gas surrounding the visible galaxy, extends approximately 1.3 million light-years in the direction of the Milky Way. In some other directions, the measurements suggest it reaches even farther, as much as 2 million light-years from Andromeda's visible center. The structure isn't uniform. It appears to be layered. An inner, more turbulent shell extending out to roughly 500,000 light-years, matching almost exactly the outer boundary of the stellar stream we just discussed. And beyond that, a smoother, hotter outer shell stretching to the full 1.3 to 2 million light-year extent. And this halo isn't empty, chemically inert gas either. Spectroscopic analysis of the quasar light passing through it reveals the fingerprints of heavy elements: carbon, silicon, oxygen. Elements that can only be forged in the nuclear furnaces of stars and then scattered into space by supernova explosions. Andromeda's halo carries the processed, enriched remnants of generations of dead stars, spread outward across more than 1 million light-years, polluting, in the most literal astronomical sense of the word, the space between galaxies with the ashes of its own stellar history. Here is the number that should genuinely stop you. Andromeda sits approximately 2.5 million light-years from the Milky Way. Its gaseous halo, in the direction pointed toward us, extends 1.3 million light-years. Our own Milky Way has a comparable halo of its own, extending outward in our direction. Do the arithmetic, and there is only one honest conclusion. The two halos are already touching. This is shocking discovery number 4 for tonight. Though by this point in the story, shock almost undersells it. We are not waiting billions of years for some future collision to begin. In the most technical, most literal sense, in terms of the actual gaseous material that constitutes a meaningful fraction of both galaxies' total mass, Andromeda and the Milky Way are already, right now, tonight, touching each other. We are, in a very real sense, standing at the edge of a shared cloud that spans the gap between two galaxies. Let's slow down and actually sit with what this discovery means, because it's easy to state the fact and move past it without absorbing how strange it actually is. If Andromeda's invisible gaseous halo were somehow rendered visible to the naked eye, if our eyes could perceive that faint, extended plasma the way they perceive the light of the bright inner disk, it would not be a smudge in one small corner of the sky. It would be, without serious competition, the single largest feature in the entire night sky. Astronomers who have modeled its angular extent estimate that a visible version of this halo would span roughly 3 times the width of the Big Dipper. One of the most recognizable, most spatially extensive patterns most people can identify in the sky, and Andromeda's true full extent would triple it. It would not look like an object you could point to. It would look like the sky itself had a texture, a soft glow occupying a significant fraction of your entire field of view, difficult to even frame as a single thing because of how much of the heavens it would actually occupy. This is worth returning to something we established earlier. The naked eye visible portion of Andromeda, that 1-degree smudge, the small cloud Al-Sufi described in the year 964, represents roughly 1/6 of the bright photographable disk. And that bright disk, in turn, sits at the very center of a structure that extends through stellar streams and then through invisible plasma to nearly 2 million light-years in some directions. If you tried to express the naked eye visible portion as a fraction of the galaxy's true total footprint, including its gaseous halo, the number becomes almost meaningless. A fraction so small it stops communicating anything except you are seeing almost none of what is actually there. And there's something quietly profound in the fact that this touching halo was discovered using quasars, some of the most distant, most ancient light sources in the observable universe, as instruments to measure something much closer to home. Astronomers pointed their most sensitive spectrograph not at Andromeda directly, but at 43 points of ancient light shining from far beyond it, and used the subtle way that ancient light was altered on its journey to map something invisible, sitting almost in our own cosmic backyard. The universe's most distant beacons used as flashlights to illuminate the space between two neighboring galaxies. There is also a sobering layer to this. That halo carries heavy elements: carbon, silicon, oxygen, forged inside dying stars and blown outward by supernovae over billions of years. Some small fraction of the gas that will eventually fall into the Milky Way, that may eventually become part of new stars, new planets, possibly new anything in our own galaxy's future, may already be Andromeda's contribution. Material processed inside a star 2.5 million light-years away, drifting for unknown ages across intergalactic space, already brushing up against the edge of our own galactic halo. We tend to think of galaxy collisions as a single dramatic future event, a specific date on a cosmic calendar, billions of years from now, when Andromeda finally arrives. But the truth, as it so often is in this kind of story, is far less like a single moment and far more like a process that has already, quietly, imperceptibly, begun. Two galaxies, each wrapped in an invisible ocean of their own gas, have already let their oceans meet. The stars themselves are still 2.5 million light-years apart, but something has already crossed that gap. We have spent this first half of tonight's exploration on Andromeda's outward reach. The vast difference between what your eyes can see and what is actually there, stretching from a 2-moon-wide smudge to a nearly 2 million light-year gaseous envelope already brushing against our own galaxy. And even this is only the visual and gaseous story. There is still the true physical body of the galaxy to measure, its actual star-filled disk, and how it compares to our own Milky Way. its trillion stars, and the astonishing scientific reversal that upended everything we thought we knew about its total mass. The monstrous black hole hiding at its very center, and the impossible ring of young stars found orbiting it against every expectation. The court of smaller galaxies that follow it through space, including one victim whose violent history may explain a strange ring of fire burning inside Andromeda's own disk. And finally, the question that started as scientific certainty and has, just this year, become one of the most fascinating open uncertainties in modern astronomy: whether Andromeda and the Milky Way, after everything, will ever actually collide at all. Let's return to solid ground for a moment, to the part of Andromeda made of actual, countable stars, densely packed enough to form the structure astronomers formally measure as the galaxy's true stellar disk. The standard measurement astronomers use for a galaxy's size is called the D25 isophotral diameter, the distance across the galaxy at the point where its surface brightness drops to a specific, standardized threshold. For Andromeda, this comes out to approximately 46.56 kiloparsecs, or, converted into a number that means something on a human scale, approximately 152,000 light-years. For comparison, our own Milky Way's stellar disk is generally measured at somewhere between 87,000 and 100,000 light-years across, depending on which study and which method you consult, with some more recent analyses suggesting it may be somewhat larger than the classical figure once thought. Even taking the more generous end of that range, Andromeda's disk, at roughly 152,000 light-years, is close to 1.5 times wider than our own galaxy. For most of the 20th century, astronomers actually believed the gap was far larger than that. The going assumption, for decades, was that Andromeda was 2 to 3 times the size of the Milky Way, a genuine giant, towering over our own comparatively modest galactic home. It took more precise modern measurement to bring that estimate down to the current, still impressive, but more moderate 1.5 times figure. We'll return to this pattern of humbling revision shortly, because it turns out Andromeda's size wasn't the only long-held number that needed correcting. Its mass needed correcting too, and in a far more dramatic way. For now, let's simply sit with the physical picture: a disk 152,000 light-years across, inclined to our line of sight by approximately 77 degrees, meaning we see it almost, but not quite, edge on, which is exactly why photographs of Andromeda show that beautiful, elongated oval shape, laced with dark dust lanes cutting across its face, rather than the more familiar face-on pinwheel shape that images of other spiral galaxies often show. We are looking at Andromeda from an angle that happens to be extraordinarily photogenic, almost as if the universe had arranged the geometry specifically for us. To really understand what 152,000 light-years of galaxy actually contains, it helps to walk through the structure the way an astronomer would. At the center sits the bulge, a dense, roughly spherical concentration of stars, mostly old, mostly what astronomers classify as population 2 stars, stars formed early in the galaxy's history, poor in the heavier elements that later generations of stars, formed from recycled material, would come to contain. This bulge is where the barred structure we mentioned earlier resides. That rod of stars, angled 55 degrees from the disk's long axis, discovered not through visible light, but through the infrared vision of the Spitzer Space Telescope, which can see through the obscuring dust that hides the galaxy's innermost structure from ordinary cameras. Radiating outward from that central bulge are the spiral arms. Vast, curving lanes traced not primarily by faint old stars, but by the bright, young, hot stars and glowing hydrogen clouds that mark active regions of ongoing star formation. Astronomers call these 8 high regions, pockets of hydrogen gas ionized by the intense ultraviolet radiation of newborn massive stars, glowing with a characteristic reddish light. It is these regions, strung along the spiral arms like beads on a curving thread, that give a spiral galaxy its recognizable pinwheel structure in photographs. One of these regions deserves special attention, because it's strange enough that it has its own name among astronomers: the Ring of Fire. Sitting at a radius of roughly 32,000 light-years from Andromeda's core, this is an unusually intense, unusually well-defined ring of active star formation, far more organized and far more energetic than the typical scattered pattern of star-forming regions found along ordinary spiral arms. It is, in effect, a nearly complete circle of newborn stars burning bright in Andromeda's disk. Rings like this don't typically form on their own through the ordinary quiet processes of galactic evolution. They are usually the signature of something violent, and later tonight we'll return to a specific suspect. A small, dense, battered companion galaxy with a history that reads almost like a crime scene, whose past collision with Andromeda's disk may be exactly what compressed enough gas in exactly the right ring-shaped pattern to ignite the ring of fire we see burning there today. Beyond the visible stars entirely, Andromeda's disk contains a staggering quantity of raw material still waiting to become stars. At least 7.2 billion solar masses of neutral hydrogen gas spread through the interstellar medium. The vast, thin material filling the space between existing stars. That's not 7.2 billion stars. That's 7.2 billion times the mass of our own sun, in gas alone, still available as raw fuel for generations of star formation yet to come. This is the anatomy of the physical galaxy. The part any deep photograph can capture, the part that fits the traditional astronomical measurements astronomers have refined over a century. A disk 1.5 times wider than our own. A barred core. Spiral arms threaded with star-forming regions. A mysterious ring of intense star birth, likely scarred into existence by a collision. Billions of solar masses of gas, still waiting. And inside all of that disk, spread across those 152,000 light-years, sits a number of individual stars so large that even astronomers, who deal in cosmic scales for a living, generally just round it to the nearest convenient figure, 1 trillion. The traditional, most commonly cited figure for Andromeda's star count is 1 trillion, 10 to the 12th power. For comparison, our own Milky Way is generally estimated to contain somewhere between 100 billion and 400 billion stars, with 250 billion serving as the most frequently cited middle estimate. Even using the higher end of the Milky Way's range, Andromeda holds roughly 4 times as many stars as our own galaxy, packed into a disk only about 1.5 times wider. In 2025, the Hubble Space Telescope completed something called the PAST survey, a panoramic mosaic that, for the first time, resolved approximately 200 million of Andromeda's individual stars as distinct points of light, rather than blended together into the smooth glow that lower resolution images produce. 200 million stars, individually counted and catalogued. And that staggering number represents roughly 1 out of every 5,000 stars actually present in the galaxy. If you tried to count every single star in Andromeda yourself, 1 per second, without ever stopping to sleep or eat, the task would take you approximately 32,000 years. For a sense of scale, every star visible to the naked human eye, from every location on Earth, across an entire human lifetime of looking up at the night sky, adds up to roughly 9,000 individual stars. Andromeda holds, within its own boundaries, something on the order of 100 million times that number. For every human being who has ever lived, and current estimates place that number at roughly 117 billion people across the entire span of human history. There are approximately 8.5 stars waiting in Andromeda. Every person who has ever drawn breath matched against a private handful of Andromeda's stars, and there would still be more than enough to go around, several times over. The star count, remarkably, has stayed fairly stable across decades of study. What has not stayed stable? What underwent one of the more dramatic scientific reversals in recent local group astronomy is Andromeda's total mass. And this is where the story gets genuinely humbling, in exactly the way this channel keeps returning to, again and again. Not because scientists were foolish, but because the universe simply does not give up its true measurements easily, even to careful, rigorous, well-intentioned researchers working with the best instruments of their era. For most of the past several decades, the standard assumption among astronomers was that Andromeda was significantly more massive than the Milky Way. Not just slightly larger, but genuinely dominant, holding perhaps 2 to 3 times our own galaxy's total mass, estimated at around 2.5 trillion solar masses when you include stars, gas, and the invisible dark matter that makes up the overwhelming majority of any galaxy's true gravitational mass. Then, in 2018, a team of researchers led by Prajwal Kafla at the University of Western Australia took a different approach. Rather than relying on earlier estimation methods, they measured the escape velocity required for the fastest moving stars in Andromeda's outer halo to break free of the galaxy's gravity entirely. That escape velocity, precisely measured, places a hard mathematical constraint on how much total mass the galaxy must contain to hold those stars in orbit at all. The results stunned much of the field. Kaffel's team calculated Andromeda's total mass at approximately 800 billion solar masses, roughly 1/3 of the previously assumed figure, and remarkably close to parity with our own Milky Way's estimated mass. For decades, astronomers had been operating under the assumption that Andromeda was the dominant giant of the local group, with the Milky Way as its comparatively modest little sibling. The 2018 measurement suggested something very different. 2 galaxies, roughly matched in mass, orbiting each other as something closer to equals. The scientific community's own language at the time captured the magnitude of the shift. The Milky Way, one popular summary of the finding put it, was no longer the little brother. But the story didn't end there. And this is worth sitting with, because it's a genuinely honest picture of how science actually works, rather than the tidy, settled fact version most documentaries prefer to present. Following the 2018 revision, further research through the early 2020s, incorporating additional data and refined modelling techniques, pulled the estimate back upward again. The most current synthesis places Andromeda's total mass at approximately 1.5 trillion solar masses, with an uncertainty of plus or minus roughly 200 billion, likely still somewhat more massive than the Milky Way. But nowhere near the 2 to 3 times dominance once assumed, and nowhere near as settled as any single number might suggest. It's worth pausing on this mass revision specifically, because it illustrates something valuable about how astronomy, how science generally, actually operates far removed from the confident, unchanging certainty that popular presentations often imply. The reason Andromeda's mass proved so difficult to pin down comes down to a simple, frustrating fact. The overwhelming majority of any large galaxy's mass isn't visible at all. Stars and gas, everything we can actually see and photograph, typically account for only a small fraction of a galaxy's true gravitational mass. The rest is dark matter, an invisible, undetectable by direct observation form of matter whose presence can only be inferred indirectly through its gravitational effects on the things we can see. Measuring dark matter means measuring motion. How fast do stars orbit at different distances from the galactic center? How fast would a star need to be moving before the galaxy's gravity could no longer hold onto it at all? Every method for estimating a galaxy's total mass is, in one way or another, an indirect inference built from watching how visible objects move under the influence of an invisible force. And different methods, using different tracer stars, different distances from the center, different statistical assumptions about the shape of the invisible dark matter halo, can produce meaningfully different answers, even when every individual team involved is doing careful, rigorous, honest science. This is not a story of scientists being wrong. It's a story of scientists doing exactly what science is supposed to do, making the best estimate possible with the tools and data available at the time, then revising that estimate, sometimes dramatically, as better tools and better data become available. The 2018 escape velocity measurement wasn't a refutation of earlier work out of carelessness. It was a genuinely different, in some ways more direct, method producing a genuinely different answer, exactly the kind of course correction that moves a field of knowledge forward. And the honest current state of the science, as of the most recent synthesis, is this. Andromeda is probably somewhat more massive than the Milky Way. Probably. Not 2 to 3 times more massive, as once assumed. Not perfectly equal, as the 2018 measurement briefly suggested. Somewhere in between, with real uncertainty still attached to the number, and with a strong likelihood that future measurements will refine it further still. We don't know the exact figure, but the not knowing, in this case, tells its own story, about how even something as fundamental as a galaxy's total mass, the very thing that defines how large and how gravitationally dominant it is, remained genuinely uncertain and actively revised within living memory, within the past decade. Not in some distant, pre-telescope past, but in ongoing, current research, still being refined as recently as 2025. Now let's turn to something that sits at the very heart of that mass, literally. Because buried in the exact center of Andromeda's bulge, hidden behind the ordinary starlight of the galaxy's core, is an object whose own scale is difficult to comprehend, wrapped in one of the strangest unsolved mysteries in modern astrophysics. At the true center of Andromeda's galactic bulge sits a supermassive black hole, designated M31 by astronomers. Its mass, based on precise measurements using the Hubble Space Telescope's spectroscopic instruments, comes out to somewhere between 110 million and 230 million solar masses, with the most commonly cited figure landing at approximately 140 million times the mass of our own Sun. For comparison, our own Milky Way's central black hole, Sagittarius A, has a mass of approximately 4.3 million solar masses. Andromeda's central black hole is roughly 35 times more massive than the one anchoring our own galaxy. Try to hold that scale for a moment. Take our Sun. Already, at its own size, more than 1 million times the volume of Earth, and compress its mass down through gravitational collapse into a single point. Then multiply that collapsed mass by 140 million, the resulting object's event horizon, the boundary beyond which nothing, not even light, can escape its gravitational pull. Would, if you place this black hole at the center of our own solar system in place of the Sun, extend roughly 2 3/4 astronomical units outward in every direction, far enough to completely swallow Mercury, Venus, Earth, and Mars whole, along with their entire orbits, and reach out into the inner edge of the asteroid belt beyond. Everything familiar about our inner solar system, every rocky planet, every world we've ever sent a spacecraft to, every place life as we know it could exist, would fit entirely inside the crushing boundary of Andromeda's central black hole with room to spare. This alone would be a remarkable enough discovery for one night. But M31 comes wrapped in a mystery stranger than its size alone. One that puzzled astronomers for over a decade before a genuinely elegant solution emerged. In 1993, Hubble Space Telescope observations of Andromeda's very center revealed something that made no sense under any conventional model of how galaxies work. Rather than a single, sharp point of light marking the galactic nucleus, the expected signature of a dense concentration of stars surrounding a central black hole, the images showed 2 distinct concentrations of light. Astronomers labeled them P1 and P2, separated from each other by a mere 1.5 parsecs, somewhere around 4 9/10 light years. This was deeply strange, because 2 separate star clusters sitting that close together, under any standard model of gravitational dynamics, should merge into a single structure within a few 100,000 years. A cosmic eye blink compared to the billions of years Andromeda has existed. And yet there they were, 2 apparently distinct concentrations, stubbornly refusing to merge, sitting right at the presumed location of the galaxy's central black hole. The resolution came from the astrophysicist Scott Tremaine at Princeton, and it is one of those explanations that, once you hear it, feels almost obvious in retrospect. The kind of elegant reframing that this channel keeps finding, again and again, at the heart of the universe's stranger puzzles. P1 and P2, Tremaine proposed, were not 2 separate star clusters at all. They were 2 ends of a single structure, an elliptical, eccentric ring of old, cool, red stars orbiting the central black hole, seen from Earth nearly edge-on. Because the ring is elliptical rather than circular, and because we view it from an angle that compresses its true shape, the near side and the far side of that single ring appear, from our vantage point, as two separate bright points rather than one continuous circle. It wasn't two hearts. It was one heart, shaped like a ring, viewed at an angle that made it look like two. But even after this elegant resolution, one more puzzle remained. And this one, astronomers still consider genuinely unsolved. Nested inside P2, in the region immediately surrounding the black hole itself, Hubble's Space Telescope imaging spectrograph detected something that should not exist there at all. A compact disk of more than 400 hot, young, blue stars, packed into a region smaller than a single light-year across, orbiting M31 at speeds of roughly 1,000 kilometers per second, something in the neighborhood of 3.5 million miles per hour. At that velocity, a star could circle the entire circumference of planet Earth in about 40 seconds. It could cross the distance to our own moon in roughly 6 minutes. Here's why this shouldn't exist. The tidal forces immediately surrounding a supermassive black hole are, under standard models of star formation, powerful enough to tear apart the loose clouds of gas and dust that normally collapse to form new stars. Star formation, as astronomers understand it, requires gas to cool and gently collapse under its own gravity. A slow, delicate process that a black hole's crushing gravitational tides should make essentially impossible in the immediate vicinity of the event horizon. And yet these 400 blue stars are young. Astronomers estimate the disk at only around 200 million years old, a small fraction of Andromeda's total age, meaning they somehow formed, or at least arrived, in one of the most gravitationally hostile environments in the entire galaxy. How several hundred young stars ended up in a tight, fast-orbiting disk wrapped directly around a black hole with 35 times the mass of our own galaxy's central monster remains one of the genuinely open puzzles of galactic astronomy. We don't know. But the not knowing, once again, is where some of the most interesting ongoing research in this field currently lives. Andromeda's single monstrous central black hole is not the only one hiding within the galaxy's boundaries. It is, in fact, only the most massive member of a much larger hidden population. In 2013, the Chandra X-ray Observatory identified 35 stellar mass black holes scattered throughout Andromeda's disk. Objects formed from the collapse of individual massive stars at the end of their lives, each holding a mass somewhere in the range of a few to a few dozen times our own Sun, rather than the 100 million plus solar mass scale of M31 itself. At the time of discovery, this was the largest confirmed population of stellar mass black holes identified in any galaxy beyond our own. And in 2022, astronomers went further, confirming something genuinely rare, an intermediate mass black hole. A category that sits in the poorly understood gap between ordinary stellar mass black holes and true galaxy-anchoring supermassive ones. Discovered inside the stripped, shredded nucleus of a former satellite galaxy that had once orbited Andromeda before being torn apart. This remains one of only a small handful of unambiguous intermediate mass black hole detections confirmed anywhere in the universe. Layer this together, and the picture that emerges is of a galaxy riddled, top to bottom, with the gravitational remnants of collapsed stars and consumed neighbors. A monstrous 140 million solar mass anchor at the true center, wrapped in a genuinely unsolved ring of stars that shouldn't exist there, surrounded by dozens of smaller stellar mass black holes scattered through the disk, and at least one intermediate black hole marking the grave of a smaller galaxy that Andromeda has already fully consumed. Which brings us, naturally, to the rest of that court. The smaller galaxies still orbiting Andromeda today, and the violent history that may explain one of the strangest features we found earlier in its disk. Andromeda does not travel through space alone. It commands a retinue. More than 20 known dwarf satellite galaxies, gravitationally bound to it, orbiting at various distances, part of the same local group structure that includes our own Milky Way and its own retinue of smaller companions. The full local group, taken together, spans roughly 10 million light-years in diameter, containing somewhere between 30 and 40 known galaxies of varying sizes, with Andromeda standing as the largest single member of the entire assembly. Two of Andromeda's companions are visible, even in relatively modest wide-field photographs, flanking the great galaxy's bright disk like attendants. M32, formerly catalogued as NGC 221, is a compact elliptical dwarf galaxy, sitting at almost exactly the same distance from us as Andromeda itself, roughly 2.5 million light-years away, but measuring only about 6,500 light-years across. A small fraction of Andromeda's own vast 152,000 light-year disk. M32's small size, though, is not necessarily its original size. Astronomers believe M32 is not a naturally small galaxy, but rather the stripped, compressed remnant core of what was once a considerably larger galaxy. One that plunged directly through Andromeda's disk at some point hundreds of millions of years ago, in an encounter violent enough to strip away the outer layers of the smaller galaxy entirely, leaving only its dense central core intact, compacted and battered, now orbiting as the small compact elliptical we observe today. And here is where the story circles back to something we examined earlier tonight, the Ring of Fire. That unusually intense, unusually well-organized ring of active star formation, sitting at a radius of roughly 32,000 light-years from Andromeda's own core. Rings like this are not the ordinary product of quiet galactic evolution. They are, in most cases, the direct signature of a collision, a smaller galaxy punching through the disk of a larger one, compressing gas ahead of it in a shockwave that radiates outward and eventually collapses into exactly the kind of tight, circular pattern of intense star formation astronomers observe in Andromeda today. M32's likely history: a once larger galaxy that plunged directly through Andromeda's disk, stripped down to its compact, surviving core by the encounter, lines up remarkably well with the kind of collision that could produce a ring like this. The violence that reduced one galaxy to a battered fragment orbiting its much larger neighbor may be the very same event that lit the Ring of Fire still burning inside Andromeda's disk today. A crime and its evidence, both still visible, still orbiting the scene, 2.5 million light-years away. Andromeda's other prominent companion, M110, formerly NGC 205, presents a gentler picture. A dwarf elliptical galaxy, larger and more elongated than M32, and unusual among dwarf ellipticals for containing visible dust lanes and pockets of young stars. Features far more typical of active spiral galaxies than of the generally quiet, gas-poor dwarf ellipticals astronomers usually catalogue. Beyond these two, Andromeda's court includes a long list of smaller companions: NGC 147, NGC 185, a numbered sequence of dwarf spheroidal galaxies running from Andromeda I through Andromeda XXViet, along with several others still being studied and catalogued. Slightly beyond Andromeda's own immediate court, but still bound within the larger local group structure, sits the Triangulum Galaxy. M33, the third largest galaxy in our cosmic neighborhood, holding roughly 40 billion stars across a disk about 60,000 light-years wide, with a total mass of approximately 50 billion solar masses. Some evidence suggests Triangulum may itself be gravitationally bound to Andromeda specifically, a satellite of the satellite-commanding giant caught in its own long, slow orbital dance around the larger galaxy. This is Andromeda's true court. More than 20 known dwarf companions, a battered former giant reduced to a compact elliptical fragment, a possible third largest galaxy satellite of its own, and the scattered stellar wreckage of however many smaller systems have already been fully absorbed and forgotten, woven permanently into that 500,000 light-year stream of stars we discussed earlier. And now, having measured Andromeda's true visual scale, its true physical size, its trillion stars, its monstrous and mysterious central black hole, and the court of smaller galaxies that follow it, we arrive at the final discovery. The one question that used to have a confident, settled answer, and that has, within the last year, become genuinely, fascinatingly uncertain again. Here is something unusual about Andromeda among nearly every other galaxy astronomers have ever measured. It is coming toward us. The overwhelming majority of galaxies in the observable universe are moving away from the Milky Way, their light stretched toward longer, redder wavelengths by the ongoing expansion of the universe itself, a redshift in astronomical terms. Andromeda is one of only about 100 known galaxies, out of the billions catalogued, that shows the opposite signature. A blue shift, indicating it is moving toward us rather than away at a measured velocity of approximately 110 kilometers per second. Fast enough, if that speed were somehow translated to travel across the surface of the Earth to cross the entire continental United States in about 40 seconds. For decades, the scientific consensus built around this approach velocity was about as close to settled fact as anything in galactic astronomy gets. A landmark 2012 study, led by Roland van der Marel, using precise Hubble measurements of Andromeda's actual motion across the sky, calculated that the two galaxies would begin their first close pass in approximately 4 to 4.5 billion years, with a complete merger. The two spiral galaxies fully combining into a single, unified structure, finishing around 6 billion years from now. The resulting galaxy would no longer be a spiral at all. It would settle, over time, into a giant elliptical galaxy, informally nicknamed by astronomers as Milkomeda, or sometimes Milkdromeda, a portmanteau marking the end of both galaxies' individual spiral identities and the beginning of something new. This was the story told in nearly every documentary, every planetarium show, every popular science article about the future of our galaxy for over a decade. A settled fact, a countdown already running. Then, in 2025, a team led by Til Sawala published a new analysis in the journal Nature Astronomy that complicated the picture in a genuinely fascinating way. The earlier 2012 prediction had modelled the future motion of just two galaxies, Andromeda and the Milky Way, treating the rest of the local group as a negligible background detail. Sawala's team incorporated something the earlier study hadn't fully accounted for: the gravitational influence of the Milky Way's own large satellite, the Large Magellanic Cloud, and Andromeda's likely companion, the Triangulum Galaxy, both pulling on the two giants in ways that meaningfully alter the long-term outcome. The effects, it turns out, work in opposite directions. Including Triangulum in the simulation pulls Andromeda somewhat more strongly toward the Milky Way, increasing the odds of an eventual merger. Including the Large Magellanic Cloud pulls the Milky Way itself sideways, off the collision course the simpler two-body model had assumed, decreasing the odds of a merger. These two effects, in Sawala's more complete modelling, very nearly cancel each other out. The result, across the full range of realistic simulations incorporating the actual complexity of our local group, the probability that Andromeda and the Milky Way ever actually merge within the next 10 billion years comes out to somewhere close to 50%. Essentially a coin flip. And even among the simulated scenarios where a merger does eventually occur, the timeline shifts considerably later than the earlier estimate. A median of roughly 7.6 billion years, rather than the 4 to 4.5 billion years the 2012 study proposed. This is the final discovery of tonight's journey, and in some ways the most quietly remarkable one. Something treated for over a decade as essentially inevitable. A certainty confidently stated in documentary after documentary, article after article, has, within the past year, genuinely opened back up into real scientific uncertainty. Not because anyone made an error, because a more complete, more careful model, incorporating gravitational players the earlier analysis had reasonably simplified away, revealed that the true answer is more delicately balanced than anyone previously appreciated. We don't know if it will happen. But we finally understand, with far more honesty than we did a decade ago, exactly how close that balance actually is. It's worth pausing, too, on what collision would even mean in the scenario where it does occur. Because the word itself carries a misleading, almost violent implication that doesn't match the physical reality at all. Stars, even inside a densely packed galaxy, are separated from their neighbours by staggering distances relative to their own size. The distance between our Sun and its nearest stellar neighbour is roughly 30 million times the Sun's own diameter, comparable, in relative scale, to two swarms of gnats, each scattered across 100 miles of open sky, slowly drifting through one another. When two galaxies collide, in the sense astronomers use the word, individual stars almost never actually strike each other. What collides is gravity and gas, and the overall shape of two vast structures passing through and around one another across hundreds of millions of years. Not cars crashing, but something closer to two soft, slow-moving clouds of smoke gliding silently through each other in the dark. If the merger does proceed roughly along the lines the classical model describes, Andromeda would begin visibly filling more and more of the night sky, starting somewhere around 3,750,000,000 years from now, its disk warping under mutual tidal forces during a first close pass sometime between 3.85 and 4.5 billion years out, flinging enormous tidal tails of stars and gas outward, compressing gas clouds violently enough to ignite. Entirely new bursts of star formation. The two galaxies would then swing past each other, slow down under their mutual gravity, and fall back together in a long, repeating orbital dance across further billions of years before finally settling, somewhere in the range of 6 to 8 billion years from now, into the single elliptical galaxy astronomers already have a nickname ready for. And through all of it, even in the scenario where the merger does occur, our own sun and its planets would almost certainly survive intact, flung, quite possibly, into a wider, different orbit within the newly forming elliptical galaxy, but not destroyed, not struck by anything, simply relocated over billions of years to a new position in a new kind of galaxy, while the sun itself, by that point long since finished with the peaceful stability of its current life, moves through the final stages of its own stellar story, regardless of whatever is happening to the galaxy around it. We've covered an enormous amount of scale tonight. Light years and solar masses and trillions of stars, numbers that, spoken aloud, tend to blur together into a kind of pleasant, meaningless static. So let's do something different. Let's shrink all of it down, together, to something you could actually hold in your hands. Picture the Milky Way. Our entire galaxy, every star we've ever seen, our sun, our solar system, all of it, shrunk down to the size of an ordinary coffee cup sitting in front of you. On that scale, our sun would be smaller than a single bacterium, utterly invisible, lost somewhere in the ceramic. The distance to the nearest star beyond our own sun would be a few millimeters, almost nothing on this scale, a fingernail's width of empty space, separating one invisible speck from the next. Now picture Andromeda on that exact same scale. It would be a second coffee cup, slightly larger than the first, sitting on the same table, roughly 40 meters away, about the length of an Olympic swimming pool. Two cups, separated by the length of a pool, and in between them, almost nothing. A faint scattering of a few tiny crumbs, representing the handful of dwarf galaxies drifting in the space between the two giants. But here's the detail that this whole night has been building toward, even at this scale. A coffee cup 40 meters from another coffee cup. The invisible halos surrounding both cups, the vast gaseous envelopes Project Amiga discovered, would already be overlapping in the middle of that table. Two objects small enough to hold in one hand, separated by the length of a swimming pool, and their true extent, at true scale, is already touching. Try one more version of the same idea. Imagine the Milky Way as a city the size of London, one of the largest, most sprawling metropolitan areas on Earth. On that same scale, Andromeda would be a slightly larger city, roughly the size of Tokyo. And in this analogy, every single one of Andromeda's trillion stars becomes a single person. A city of 1 trillion people, each one separated from their nearest neighbor by roughly 30 million kilometers of empty space. A Tokyo where every single resident lives, essentially, alone, in a private darkness so vast that the idea of a crowded city becomes almost the opposite of what 1 trillion stars packed into one galaxy actually feels like if you could stand inside it. And now, one final piece of scale. Not of space, but of time. The light entering your eyes right now, if you were to step outside tonight and find that same faint smudge that Al-Sufi described 11 centuries ago, left Andromeda roughly 2.5 million years ago. If you compressed the entire span of human civilization since the invention of agriculture, 12,000 years of cities, writing, empires, everything we generally think of as history, down into a single minute, that light has been traveling continuously, without pause, for 3 hours and 40 minutes before that minute even began. If a single day represented 100 years, the light left Andromeda 68 years ago and has been in flight, uninterrupted, ever since. Every photon of that light traveled a distance of roughly 25 quintillion kilometers to arrive at your eye tonight. 25 followed by 18 zeros. And during that entire 2.5 million year journey, every human ancestor who ever lived evolved, generation by generation, from an ape-like hominin scattered across the plains of East Africa into whatever you are, sitting here, tonight, receiving the final photon of a journey that began before your species even existed in its current form. If Andromeda somehow vanished at this exact instant, if something impossible happened to erase it entirely, right now, as you listen to these words, we would not know. Not for another 2.5 million years. Every human being who will ever be born across the next 100,000 generations will look up and see, essentially, the same picture you could see tonight, because the light carrying that picture to Earth is already more than 90% of the way here, already committed, already in flight, regardless of anything that might happen to its source between now and the moment it arrives. There is something worth sitting with, now that we've walked through the entire true scale of Andromeda, from the faint two-moon smudge your naked eye can register to the nearly 2 million light-year gaseous halo already brushing against our own galaxy's edge. The galaxy never changed, not once, across this entire night's exploration. Every single figure we've discussed, the 6-moon disk, the 500,000 light-year stellar stream, the touching halos, the trillion stars, the 35 times more massive black hole, the uncertain collision. All of it was already true, unchanged, for millions and billions of years before a single human being existed to measure any of it. Andromeda was always this large, always this strange, always already touching us, in the gaseous sense, long before Project Omega's 43 quasars revealed the fact in 2020. What changed was not the galaxy. What changed was us, our instruments, our patience, our willingness to keep looking past the point where the naked eye gives up, past the point where a single photograph seems to show the whole picture, past the point where a settled scientific consensus feels finished and complete. Al-Sufi, in the year 964, looked up with nothing but his own eyes and correctly identified a real, physical object. A small cloud, he called it, and he was not wrong that something was there. He simply had no way of knowing that the smudge he was describing was the compressed, foreshortened, radically undersold visual signature of something that, if he could have somehow perceived its true extent, would have dominated a meaningful fraction of his entire night sky. Every generation since has repeated some version of the same experience. Messier catalogued it as a convenient smudge to avoid confusing with comets. Roberts photographed a spiral, and everyone confidently misread it as a solar system being born. Hubble measured a distance and got the right category of answer with the wrong precise number, off by a factor of nearly 3. Astronomers spent decades confident that Andromeda outweighed the Milky Way 2 or 3 times over, before a single 2018 measurement cut that number by more than half, only for later work to walk the figure partway back up again. An entire generation of documentaries confidently announced a collision in 4 billion years as essentially settled fact, before a 2025 study revealed the true odds sit closer to a coin flip. Every single one of these was not a failure. Each was simply the honest, best available answer, offered by careful people using the best tools they had at the specific moment they were working. And each was, in its turn, quietly, respectfully, scientifically superseded by something closer to the truth. This is not a story about human error. It's a story about scale, about the specific, humbling gap between what a limited instrument, whether an unaided human eye or an early telescope or an initial gravitational model can perceive, and what is actually, physically, permanently there, waiting patiently to be found by whatever comes next. And there is something worth treasuring in that gap, rather than something to mourn, because it means the universe does not run out. Every single time we've built a better instrument, a more sensitive camera, a more careful model, Andromeda has offered up more of itself. Not a different galaxy. The same galaxy, unchanged, simply revealing another layer of a scale that was, this entire time, patiently waiting for us to catch up to it. You are made, at the level of your own atoms, from the same material as every star inside that galaxy. Carbon forged in a stellar core somewhere. Iron forged in the death of a star large enough to end its life in collapse. The universe took roughly 9 billion years, after its own beginning, to produce the raw material necessary to eventually assemble something like you. An arrangement of atoms complex enough to build a telescope, patient enough to point it at a 2-moon-wide smudge in the sky, and curious enough to keep looking until that smudge finally, slowly, admitted the truth of its own staggering size. Picture it one more time before we close. 2.5 million years ago, on a night with no witnesses at all. No humans, not yet. Only early hominins scattered across the plains of a much younger Earth. A particular handful of photons left the surface of a star somewhere inside Andromeda's vast disk. They had no destination in mind. They simply traveled, in a straight line, at the only speed light is capable of, out into the dark. They crossed the 500,000 light-year stream of shattered dwarf galaxies. They passed through the outer edge of Andromeda's own invisible gaseous halo, and eventually left it behind entirely, continuing on through the true emptiness of intergalactic space. They crossed 2.5 million light-years of almost nothing at all. And at some point during that unthinkably long, silent, uneventful journey on the small rocky planet those photons happened to be aimed toward, something remarkable was quietly happening. Early hominins were slowly, generation by generation, becoming something else. Tools were invented. Fire was tamed. Language emerged. Civilizations rose. Entire empires were born and fell to dust, over and over, while the light kept traveling, indifferent, uninterrupted, unaware that anything on its distant destination was changing at all. And tonight, after every single one of those 2.5 million years has finally, fully elapsed, that specific handful of photons has arrived, right here, right now. Some of them, perhaps, entering your own eyes if you happen to be somewhere dark enough on a clear enough night to catch that small, faint, endlessly underselling smudge of light for yourself. You are the destination of a 2.5 million year journey that began before your species had language, before it had fire, before it had a name for itself at all. And the smudge you'd see, if you looked up tonight, is telling you the truth about almost nothing regarding what it actually represents. Not its true visual size. 6 moons wide, not one. Not its true physical extent. A stream of shattered galaxies 500,000 light-years long. Not its true reach. A gaseous ocean already touching the edge of your own galaxy, right now, tonight, while you rest. And somewhere inside that vast, trillion-star structure, 35 times more gravitationally dominant at its very center than anything anchoring our own galaxy, 400 young blue stars are still orbiting a black hole in a configuration nobody has fully explained. A battered dwarf galaxy still circles the giant that once tore through its body and reduced it to a fragment. And 2 galaxies, ours and that one, drift toward each other across a gap of 2.5 million light-years, carried by a gravitational dance whose final outcome, as of the most recent research available, genuinely, honestly, remains a coin flip. We don't know if we'll ever meet Andromeda in the deepest sense. We don't know if Milky will ever actually exist. But we know, now, with more precision and more honesty than any generation before us has ever had access to, exactly how close, how uncertain, how genuinely open that question still is. And you, small, brief, built from the same stardust as every star in that trillion-star galaxy, are the one asking it. Tonight, we explored the true scale of Andromeda. And what we found was not a single number, but a long series of quiet corrections, each one revealing more than the last. We found that the faint smudge visible to the naked eye, the small cloud Al-Sufi described in the year 964, represents only a fraction of the galaxy's true photographable size, hidden from human perception, not by distance, but by the basic physics of surface, brightness, and the limits of the human retina. We found that the bright, photographable disk itself, 6 full moons wide, is only the beginning. That a stream of stars torn from smaller, consumed galaxies stretches the true stellar structure out to nearly 500,000 light-years, and that an invisible ocean of gas reaches even farther still, extending nearly 2 million light-years in places, already touching the edge of our own Milky Way's halo tonight. We found that the galaxy's physical disk, 1.5 times wider than our own, holds roughly 1 trillion stars, 4 times our own galaxy's population, and that its total mass, once confidently overestimated by a factor of 2 or 3, was revised downward in 2018 and then partially back upward again, an honest, ongoing correction rather than a single settled fact. We found a black hole 35 times more massive than the one anchoring our own galaxy, wrapped in a ring mistaken for 2 hearts for over a decade, and orbited by 400 young stars that, by every reasonable model, should not exist there at all. We found a court of more than 20 companion galaxies, including one likely victim of a direct collision whose violent history may explain a ring of fire still burning inside Andromeda's disk today. And we found that the collision so many documentaries have treated as inevitable, a settled countdown to a galaxy called Milkomeda, was reopened just last year into genuine, honest uncertainty. A coin flip, drawn not from carelessness but from a more complete accounting of the gravitational neighbours surrounding us both. None of these discoveries changed Andromeda itself. The galaxy was always this large, this strange, this uncertain in its future. What changed, across every single one of these corrections, was simply our capacity to see it more clearly. One better instrument, one more careful model, one more patient astronomer at a time. So the next time you find that faint, unremarkable smudge of light in the northern sky, if you ever do, on some clear, dark night, far from any city glow, know that you are looking at something your own eyes are fundamentally incapable of showing you in full. A trillion stars, a black hole 35 times the size of our own, a gaseous reach already brushing against everything you know, a future that may or may not ever arrive. And know, too, that the light reaching your eyes in that moment left its source 2.5 million years ago, before anything recognizably human existed to receive it, traveling in patient silence across a gap so vast that no number spoken aloud will ever quite make you feel its true size. Only sense, faintly, the edge of it, the way your own eyes sense only the edge of Andromeda itself. You are here for a brief, improbable moment made of the same stardust as every one of that trillion stars, awake long enough to look up, to wonder, and to ask what's actually there. That is enough. Sleep well tonight, knowing that somewhere above you, a galaxy far larger than you'll ever fully see is drifting quietly closer, one imperceptible year at a time, carrying a trillion stars, a monstrous heart, and a fate still genuinely, wonderfully unwritten. Good night, and sleep well under the stars, and under everything 6 moons wide and far beyond that you cannot quite see.